Welcome to the second webinar broadcast by Castool Tooling Systems in our multi-part webinar series that will occur once a month. Please visit us at our website at www.castool.com for a schedule of events. My name is Danny Dunn and I am the Extrusion Sales Director for Castool Tooling Systems. Castool for many years has brought to the market the phrase, the tooling system. However, each component must first be separated and evaluated to ensure material, design, function are optimized for the specific application. This can only be done as it is pulled out of the process, then reinserted into the process as part of the tooling system. For this webinar, we will focus on the container and the QR container. We must first look at the container as its basic function. The container must support the billet during extrusion and withstand the pressures of extrusion. It must provide a place that uniform alloy can flow through the die. It also must dissipate auxiliary heat generated by the extrusion process, as well as make isothermal extrusion attainable. Lastly, it must manage the heat balance during extrusion. When we look at heat balance, we break it up fairly simply. There are three contributing factors as they are as follows by a simple formula of D, which is extrusion heat, equals A plus B minus C. So we start with A. This is the heat that is generated with the preheated billet, with of course an effective taper from front to back. We then introduced B, which is the heat generated during the deformation of the aluminum billet during extrusion. In figure B, the graph shows the typical pressure curve, force N versus ram displacement M. The area under the curve is where the work is being done during the deformation of the billet and is where the extra extrusion heat is being generated. We then subtract C. C is the heat lost within the container both radially and longitudinally based on an effective cooling system coupled with container zone offsets. What we're left with is of course D, which is the extrusion temperature. In this thermal image, we can clearly see that the container is imbalanced. As the liner temperature approaches the billet temperature, type 1 inflow will begin to occur. Second to this, the die by conduction through the container is hotter at the top than on the bottom. This thermal imbalance will contribute to the short life of liners, mantles, as well as poor dummy block performance. Also, physical press alignment is difficult to maintain and energy is wasted. We have looked at the effect of the container and billet skin flow. The negative effect of type 1 inflow is encouraged through excessive liner temperature. As the liner and the body reach a saturation point and the container can no longer effectively dissipate the heat generated during extrusion. On the opposite side of this coin, if the container is too cold, type B inflow will occur, which is better known as coring. If your container is thermally imbalanced, you could experience both situations, which are not good for productivity and extrusion quality. If we look at this a little bit more carefully, type 1 inflow is evident on the slide on the left. You can see the flow of aluminum from the wall of the liner and then follow it as it travels through into the pockets of the die. And then of course through the finished extrusion. The image on the right shows this billet skin actually laying on the surface of the extrusion. In this slide, we're going to get into a little bit more detail in the comparison of different container designs. In this slide, we observe what separates these three designs. First, placement of heating source or elements, thermocouple placement relative to the liner and elements, and the control system's ability to read and react to accurate readings within the container is critical to the placement of these components as they work together. Also, The element location is critical to the container body having the ability to dissipate additional temperature generated during extrusion cycle. In figure A, the thermocouple is placed in the middle of the body, which by way of the thermodynamics and cooling rates inside the housing is the hardest part of the container. Second to this, the elements are located on the OD of the body, which will not allow for adequate heat dissipation through the material to the atmosphere, allowing the body to radiate heat effectively. Also in this configuration, the container housing is heated, which has a negative effect on physical alignment as well as side cylinders and rods. Typically, supplementary air cooling on the container liner is used to control any overshoot of liner temperature. In figure B, we see the thermocouple placement has moved, but still not in the optimal location. These elements have moved centrally to the mass as they focus to heat the entire container body. The element location still creates the same thermal constraints as in figure A design, with an increased opportunity for liner overshoot. In this design, we typically see multiple zones of air cooling on the liner. In figure C, we see the container QR method. This method has the thermocouple strategically placed in 4 areas of the container, very near to the liner. The element location close to the liner is strategic, as the goal is to manage liner temperature and not container body temperature. By moving the elements close to the liner and the elements close to the liner in proximity of each other, accurate and quick response to changing temperatures in the process are achieved. Also, with this design, there is no use of air cooling, as through design and proper allocation of materials for the process, highly thermally conductive materials are used, which allow for the mass of the steel to dissipate heat generated during extrusion much evenly and quicker. It's a fact that mechanical stresses within the container and liner assembly are increased on both the liner and body with the placement of air cooling grooves. Also, the heat transfer from the liner and body is greatly reduced as the surface contact area has been compromised, which contributes to the increase of liner temperatures. In this image, we can clearly see in the QR container how relatively close proximity we have the liner OD, the thermocouple, and then the supporting heat source. We're now going to look at radial temperatures. We're going to overview 2 designs. We can see in this illustration in figure A, it is hotter on the body OD with a cooler band in the middle, third, and then a hotter zone around the liner. In figure B, the QR container heating system close to the bore and a hot zone around the bore. The cooler or green area is the body working to dissipate heat it is generated, which allows for a stable heat condition, again, with no air cooling. The slide in figure A, we see complete thermal saturation with the container designs of wraparound heating as well as heating central to the mass. This allows for no movement of heat generation during the extrusion process. Once again, heat extraction is typically done through air cooling on the body liner. In figure B, the QR method with the heat source located close to the bore and properly cast tool tapered front to back and top and bottom zones in 4 zones where applicable. Any excessive heat generated by the process is allowed to move both radially and linearly through the container, once again, without the use of any air cooling. So by example, let's look at the facts. This is an example of a 10-inch container with a 45-inch OD and 48 inches in length. It had internally heated elements placed within the central to the mass, as well as 2 zones of air cooling on the liner. That system had the ability to pull out 198,000 BTUs per hour. With a modified design to cast tool, with the elements located very close to the bore with the thermocouples, and using the mass of the body to pull the BTUs from the bore, we had the ability to pull out 652,381 BTUs of power, almost 3 times. When we talk about stress within the body, the stress near the ID of the container is between 90 and 100,000 psi, where on the OD of the body is between 18 and 20,000 psi. If air cooling grooves are required, they would be placed on the OD of the body, not on the ID. We have almost 5 times the stresses on the inside of the container, which contributes to cracking. Let's look quickly at material. Material is one of the cornerstones of designing a container. Original container bodies were supplied with 4140, ASI 4140 or 4340, or DIN number 1.6582. Now, the trend seems to be going to 1.2343, which is H11, or 1.2344, which is H13. The original extrusion container was designed with these materials in order to be a heat sink. So let's compare them. In the bottom left-hand, right-hand corner of this graph, let's compare the thermal conductivity, or Wm.K, with the 4.3 and 4.4 materials to 4340. With the 4.3 and 4.4 materials hovering at 24 WMK compared to 4140 and 4340 at 42, the 4340 material is almost twice as thermally conductive as the 1.2344 and 4.3. When we look at fracture toughness and critical crack length, which is the ductility of this material, we look at, again, the materials of 43 and 44 in comparison to 4340, and it's slightly twice the fracture toughness and ductility. When we look at the thermal expansion of 12.6 to 12.1, they're almost identical, which makes 4340 as a container body material and H11 or H13 more than compatible for what the original container design was meant to do. Let's now look at the advantages of element placement. In figure A, the elements are placed central to the container mass. The modeling shows the elements burn at a higher rate and a higher temperature. As the system tries to heat the entire mass, the result of this can cause localized annealing around the element holes. In figure B, the heating system, or the QR system, runs substantially less, as the elements run only to balance the heat between what is being generated during extrusion and what is being lost to the surrounding press tooling and press components. This leads to a reduction in energy consumption and the elongation of tooling life. When we look at moving the elements close to the body, let's actually look at a picture. In figure A, we see typical internally heated container with elements located central to the mass of the container. The thin cross-section between the element circle and the OD of the body lends itself to have heat travel the path of least resistance, outwardly. The element location relative to the bore and thermocouples increases the opportunity of cracking as the heat transfers from this outward ring of elements to the bore, and then from the bore back to this outward ring. This thermal movement contributes to the cracking of container mantles. In figure B, the QR method is observed. The heating system, thermocouples, are in the same proximity as the bore. This container will have the same thermal characteristics of a container if it is idle or in the process of extrusion. The thermal stresses are virtually eliminated, elongating both the life of the liner, the body, as well as the surrounding extrusion components. So let's look at heat dissipation. These 3 lines illustrate the heat dissipation rates during extrusion of 3 specific designs over 200 billets. The blue line is data on an externally heated container, and you can see the uneven flow of heat as the body heats and cools during process. This movement of heat with the linear direction contact with the elements burning over the annealing temperature of the material can cause not only cracking, but annealing as well. The middle black line is data captured on an internally heated container. Although much flatter, the external heated container still has spikes up and down as the lag difference due to the distance between the heating elements and the thermocouples hinders this performance and reaction time. The red line is the data that is captured on a QR container. You can also observe it is much flatter and consistent. Also, notice as well the comparison of watts dissipated. On the externally heated container, swings from less of 2,000 watts to a positive 2,000 watts. The internally heated container swings between 5,000 to 6,000 watts of heat dissipation. Where the QR container is stable at 10,000 watts, almost 5 times more than the externally heated container, and twice that of the internally heated container. What does that mean? Well, let's look at the longitudinal temperature gradients. This data has been captured over the 3 container designs over 300 billet run. Once again, the externally heated container performs poorly, with the internally container performing better, but still with spikes. However, the QR container is stable and completely linear. Let's look at that QR container. Let's look at the liner temperature, fairly stable over 200 billets at 445 degrees Celsius. We look at the body hovering around 395 to 400. This proves that the temperature being generated in the ID of the container is dissipating out, and it is quite flat. An interesting thing to note on startup, when you have the bore of the container looking similar to that of the flat process, what we find is that the actual startup of the billet, or the startup of the container, I'm sorry, what ends up happening, this dotted line represents 4 billets. You can see how quickly the blue line, that after 4 billets, the container becomes extremely stable. We see that if a container has been shut down for several days, that preheat time of the container during extrusion in order to get the bore stable causes, at times, increased scrap. As we move forward, let's look at the advantages of the vertical offset. The modeling in the side supports that the containers are hotter on the top than on the bottom, and not because heat is rising, although there is heat rising in the container in that process, but not enough to have a negative effect on anything. It's due to the heat loss through the die slide in the bottom of the press as temperature moves from the bottom of the press down through the ground. The addition of heat in a single zone on the die side of the container corrects this heat loss as it negatively affects the flow stress of aluminum through the die. We have 2 basic designs that we are producing at Catstool. The 2 most popular being the QRC. It's a 2-zone container designed for 28-inch diameter containers, 700 millimeters or less. What we find through data gathered over many installations and customer feedback is the smaller diameter containers require only 2 zones, 1 top and 1 bottom. The next one is the more popular QR container with 4 zones of heating. It's the most widely recognized design we make. This design is used on container bodies 700 millimeters or 28 inches and larger in diameter. You can see that there are clearly marked as zone 1, which is the die side bottom, zone 2, which is the die side top, zone 3, which is the entry end top, and zone 4, which is the entry end bottom. The multi-zone control of the QR container is instrumental to its function. The container prior to extrusion will be ramped up slowly, either using a Catstool warm-up panel or a set of secondary programming supplied in conjunction with our control panel. This slow ramping of preheat from plant temperature to operating temperature is critical to element life and that of the electrical system itself. This allows for any moisture to be slowly eliminated from the core of the elements prior to the application of full heat and power. The slow ramping also ensures that the shrink fit between the liner and the body is not negatively affected, which could cause premature failure of the liner and or body. The container, once preheated, will have a Catstool specified set of parameters, which is critical to its function. There will be an effective taper front to back. Second to this, there will be an offset top to bottom on the die side of this container. The offset will be based on the zone 2 top side of the container. Whatever the temperature reading is in this zone, a predetermined offset will be added to zone 1 or the bottom of the die. to compensate for any heat loss due to the die, slide, auxiliary tooling, and the plain thermal dynamics of the press. During extrusion, Zone 1 will be running between 85 to 100% of the time. Zone 2 will typically not run more than 5 to 15% of the time, where Zone 3 and 4 will run 20 to 30% of the time, maintaining the natural cooling taper of the open-ended container. Obviously, these temperatures and rates change from press to press and from container to container, hence the reason for a Castool experienced technician to be on site during startup, and once again, once or twice through the year, to examine that the extrusion conditions have not changed. So let's now take a quick look at design as it pertains to stress. The press manufacturers and customers alike now are starting to specify longer containers, which can be a great thing for recovery as well as productivity. However, they come with their own set of problems. That being hoop strength and deflection within the container and the interaction between the dummy block and the container, which is so misunderstood. In this example, we have a typical 8-inch container with a 45-inch long body, extrusion ratio of 45, pretty typical. The lines on this graph plot out the specific pressure and ram displacement in inches. So you can see they're actually quite linear and topping off at 100 KSI. When we make a design change to this container, and we now take it from 40.5 inches long to 51.5 inches long, the world slightly changes. What has changed? The specific pressure at that billet. And why? Because the longer billet has an increased flow stress due to the surface friction between the billet wall and the container wall. This plays havoc on the dummy block and container interaction as the specific pressure rises from 100 KSI to 120 KSI in this case. This is close to the design limits of most dummy blocks, as well as it translates into liner growth due to specific pressure. Let's look at it. If we look at a container length of 1 meter, and we translate that over under the same conditions to a 2-piece container design, we expect the liner to deflect 0.88 millimeters. On a three-piece container, it actually is reduced to 0.58 with the increased hoop strength. If we go all the way to the bottom of this chart and we look at 1.5 meter long container or 60 inches, on a 2-piece container, we can anticipate 1.32 millimeters of deflection. With a 3-piece container with the additional hoop strength, that's now reduced to 0.85. So what does that mean? Let's continue. If we look at that 0.88 millimeters at 1 meter, and we look at the 1.5 millimeters at 1.5 meters at 1.32 millimeters, 6000 series alloys extrude by the dummy block at 0.6 or 0.7 gap. We have a problem. You now compare that to 4340 with a 0.88 millimeter at 1 meter, and then at 8.88 millimeters, sorry. Now turn that into a 3-piece container at 1.5 meters or 60 inches. The deflection is much less at 0.85. Once again, being reminded that the dummy block, the alloy will extrude past the dummy block at 0.6 or 0.7 gap. If we take those 3 designs once again and we plot them on another graph comparing KSI, we notice that the lower the KSI is the better for the container and the least amount of deflection. The 1-piece is 216 KSI, 2-piece is 183 KSI, and the 3-piece is 163 KSI. When we look at these higher pressure containers, we can't help but look at the dummy block and container interaction. One of the 2 papers that Castool published in ET this year was the container and dummy block interaction. If you go to our website and you look under publications, you'll see that paper. It's a very good read and worth a download. Again, to touch back, the most important part of this is the dummy block interaction. We need to have a thermally stable container and a mechanically stable container. The dummy block has no idea what the ID of the container is. So we have to design a dummy block to withstand those pressures over time and pressure in relation to the alloy and the length of the container. This design is very, very important in extremely long containers. soft and hard alloys, as well as extremely long extrusion cycles. Why does this matter? It comes back to billet skin. The new HPR block with these higher specific pressures and longer containers with these soft alloys and long cycles, we observe the top two lines, starting with the blue line, which is the line under pressure of the expanded diameter of the container. The orange line is the expanded dummy block diameter. You can see, if you look down further onto the graph, at the dummy block unexpanded diameter is 209.0. Starting with the liner is 210. Under pressure, we witnessed that the dummy block expanded goes to 210.5 to 210.7 and is consistent throughout the extrusion time of 45 seconds. Second to that, we can see on the blue line, the liner at the expanded diameter as well is consistent. This is how we can control billet skin, which is type 1 or type 2 inflow. When we observe and we measure that billet skin later, we can see a very consistent liner skin after 45 billets. This narrow fluctuation of billet skin is instrumental in obtaining good, consistent surface finish on the extrusion. Lastly, let's look at power. Power consumption. These are two distinct data logs of two different design containers. Container A is an internally heated container. You can clearly see the power spikes on and off as the heating system ramps to preheat the container. Once running, there's large power swings as the container heating system turns on and off. These power spikes are not good. They're a waste of valuable energy, and they also create thermal mechanical stresses to the both container and the liner. Data log B shows the smooth and steady application of heat to the container. Then once again, the process control system takes over, which is much a lower application of power during the cycle. This data was measured over 603 billets. So lastly, with the QR container, we provide a uniform flow of alloy through the die, reduce cost of operation, reduce scrap, downtime, increase productivity, and also making isothermal extrusion more attainable. And we increase the operating life of not only the liner, the body, but all of the interacting parts with this container. Now, this container is ready to put back into the process as part of the tooling system. Thank you. You can please visit our website at www.castool.com, where this webinar will be uploaded. Also, please look at our extrusion products and select any one of those products for further information. Lastly, please go to our publications tab, where you'll see all of the technical papers that have been presented and uploaded. Thank you very much, and have a great day.